Hi, everybody, and welcome back. We're going to start off Chapter 3 today. Very exciting. Chapter 3 is about atoms, which are, of course, the building blocks of matter. Atoms are very exciting. We're going to talk about their history. We're going to talk about what makes atoms up. A lot of this will be review, but we'll also be learning some new stuff too. So let's move through the history of atoms, starting first with the history of atomic theory. And atomic theory has its roots way back in the day, thousands of years ago, back around the time of Aristotle, 2,500 years ago, when people were just walking around thinking. And so if you wanted to know 2,500 years ago what matter was made up of, what would be your method? And the honest answer is you would just guess. There were some very intelligent thinkers back then, but science wasn't really a thing. The scientific method didn't really exist. And so you pretty much guessed. You looked at the world around you and you said, this is the way I think the world works. This is what makes sense to me. If there's noises coming from the sky, they must be bowling up there. Or there must be monsters out at sea. That's what explains why these ships aren't coming back. And so there was a lot of guessing going on. The first person we're going to talk about today is a philosopher named Democritus. Now, Democritus was the first person to actually propose the idea, the notion of an atom, and this was about 400 BC, and his idea was basically that atoms are small, indivisible spheres, and the word atom came from the word atomos, which meant simply indivisible. And Democritus came to this conclusion, pretty much you can imagine kind of looking at, maybe a piece of fruit or something like that and seeing what looks like, little grains in there, or little chunks in there, or looking at a rock and seeing the small little grains in a rock and sort of being like, I wonder if there is a smallest thing. I wonder if there's a smallest possible point you can get to, right? And so that's sort of how Democritus came to his idea. And we have to remember that there is a difference between science and philosophy. When you talk about philosophers are great thinkers, and they propose great ideas. Fantastic mental experiments where you imagine that your entire existence is simply some brain in a jar or something like that. But scientists have to back it up, and that's the key difference. It's sort of like opinion versus theory. It's saying what you think versus here is what the evidence points towards. Anyone can have an opinion, but it takes a lot of agreeing evidence to form a theory. And sometimes when you're just going on opinions, it can become a popularity contest. And unfortunately, soon after Democritus, there was Aristotle. And I say unfortunately, but I don't really mean, unfortunately Aristotle was born, because Aristotle was a great thinker, great philosopher. And Aristotle kind of countered with this idea that matter was continuous. He did not buy into Democritus's idea. And so because Aristotle was a little more well-known, a little more popular, about 2,000 years go by with people believing that matter was continuously divisible. Think of a piece of paper or a leaf, and you're ripping it in half, and you're ripping it in half, and you're ripping it in half. And you've got to ask yourself, if I had small enough fingers, could I keep ripping this forever? Aristotle thought yes. Democritus thought, no, you're going to get to a point where you have the smallest possible piece of paper that you can imagine. And that's really where the two sort of separated, and unfortunately, for atomic theory, we believed in Aristotle's theory for quite a period of time. And so time passes, wars are fought, plagues decimate populations, and finally the 1700s get here, and we have better tools, more time, there's less dying going on, so things get a little bit better for us. And we start to introduce some new laws. Again, when we talk about better tools and better equipment, people actually are living longer, and they're staying, they're not working to survive. We have better medicine, we take better care of ourselves. So people have time to think about these sorts of things. We have better telescopes, better pieces of scientific equipment, and so people start to be able to really analyze matter. And the law of conservation of mass is established in 1789 by Antoine Lavoisier, a Frenchman. And basically the law of conservation of mass states that matter can neither be created nor destroyed. For example, a famous example is the burning log, where you burn a log and you look at it and you're like, there's nothing left. We must have destroyed the log. We must have destroyed the matter here. Clearly it's gone. But what Lavoisier found by careful measurement was that in burning the log and recollecting all the smoke and all the soot and everything else, you could account for every single gram of mass. Now, we do know now that you can convert mass into energy via nuclear reaction, but in any ordinary chemical reaction, all mass is accounted for during the chemical reaction. Next is the law of definite proportions, and this was proposed by Joseph Proust, I think another Frenchman, in 1806. And basically what Proust said was that a chemical compound contains the same elements in exactly the same proportions by mass regardless of the size of the sample or source of the compound. So that salt is always 39.34% sodium and 60.66% chlorine by mass. And the reason for that Proust did not know at the time, was that salt has a chemical formula. We know that now, right? Like you have one sodium and you have one chlorine, and when they go together, it's a 1-to-1 ratio, NaCl. So that ratio of mass, a sodium atom weighs a certain amount, a chlorine atom weighs a certain amount. And so when they go together, that's why the ratio is always the same. We didn't know about chemical formulas at the time, but this was kind of a major establishment that there was something going on, that no matter where this substance comes from, it's put together in exactly the same way, right? And the law of multiple proportions was later proposed by a scientist, well, not a scientist really, a school teacher who was a pretty scientist. Yeah, he's a scientist. Law of multiple proportions, which states that if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio, not ration, of small whole numbers. And what this basically says is simple enough that when you put these elements together, and you sort of have a mass ratio, say for nitrogen, of 14 to 16, and you sort of lock in the lowest ratio. 14 is 1 for nitrogen, 16 is 1 for oxygen. It'll always be a multiple of that ratio. It'll always be a whole number multiple. So you can have 2 to 1, or 1 to 2, or 2 to 2, or 2 to 5. But it's always a whole number multiple. And again, what Dalton doesn't know at this point is that it's because of chemical formulas, that these atoms are coming together in small whole numbers. Again, you got to remember at this time, they have no idea that atoms exist. Like, they still are sort of like, we're just playing around with matter, and they're finding these sorts of things out just by trial and error. But it seems really simple to us. We're like, how can these dummies not figure it out? But it's because they didn't have any idea how atoms worked or how chemical compounds were put together in terms of whole atoms. And so that's why we have these whole number ratios. But Dalton, crazy smart guy. So John Dalton is going to be the first scientist we really talk about quite a bit. John Dalton in the early 1800s, 1808, actually proposes, based upon experimentation that had taken place before, of course, that of Lavoisier, that of Proust. He comes up with an atomic theory, the first atomic theory based on scientific evidence. Of course, not all of that scientific evidence was his, but he is kind of the one who pulls it together and comes up with 5 rules that describe how atoms will work. Rule 1, all elements are composed of tiny particles called atoms. Seems pretty straightforward. No arguments there. Number 2, atoms of the same element are identical. So if you have 2 copper atoms, they should be exactly alike. And different elements will have different atoms. If you have a copper atom and an oxygen atom, they will not be alike. That's rule 2. It seems to make sense to us. But this is not entirely true. We now know it's not entirely true because you have different isotopes. You can have, for example, oxygen 12 and oxygen 13. They have the same number of protons, the same number of electrons. They differ in the number of neutrons. Good job. I heard someone, I think it was in the back, say it. But different numbers of neutrons. So they're not exactly the same. But we'll talk more about that later. Atoms can't be created, destroyed, or broken into parts. Is that true? No. Dalton did not know about electrons, protons, the nucleus, any of that. So at the time, it makes perfect sense. And really, if you just look at chemical reactions, it still makes sense. But we know now that, of course, we have nuclear fission, that we have these teeny tiny little particles that make up the atom, and the nucleus. And the nucleus can be split and all that sort of stuff. So we now know better. But at the time, it was a pretty good idea. Atoms of different elements can chemically combine with one another in simple whole number ratios to form compounds. All that means is chemical formulas, right? Water is H2O. There's a reason why the ratio of hydrogen to oxygen is always the same. It's because you have 2 hydrogens and 1 oxygen. It's not some kind of random mathematical coincidence. It's because water is made up of the same number of atoms, 2 hydrogens and 1 oxygen, each and every single time, right? Rule 5. Chemical reactions occur when atoms are separated, joined, or rearranged. But the atoms do not change their identity. So when you have a chemical reaction occur, you are not destroying the atoms. You are simply pulling them apart, you are breaking their chemical bonds, and then you are forming new ones. But you're not changing what the atoms are. And atoms are the smallest pieces of an element that still retain the properties of that element. That's kind of the definition of an atom. Atoms are super small. About 100 million copper atoms in a row would only be a centimeter long. So think about that. 100 million in a row would only be about a centimeter. And we can actually see atoms now with surface tunneling microscopes and electron microscopes. We can actually see the individual atoms, and you can see an example of that in your book on page 66, or just type in surface tunneling microscope or electron microscope into your web browser, and you can see some cool pictures and videos. Here's an actual picture of what that might look like. Again, we are not taking like a camera picture of atoms, but we are getting a virtual representation of how they're arranged. We might be bouncing electrons off of a row of atoms to get a picture of what they look like, similar to how you see what the bottom of the ocean looks like, right? You get sonar pictures of it, at least until you dive down there and take a look. And the big thing to take away from this is that atomic theory is not set in stone. Atomic theory is constantly changing. Dalton is kind of setting down the base rules here in this first section, but we are going to keep evolving. And we are still evolving. If you pay attention to the news, we're trying to find out more and more about how the inside of the atom works and how the nucleus works and what sort of particles all make up an atom. Lots and lots of media attention kind of goes into colliders and things like that, and the discoveries they're making, dark matter, antimatter, all that sort of stuff. So we're still interested. And that's where we're going to stop. We will look next time at the structure of the nuclear atom. So we'll see you then. Thanks for watching.